Hello students, welcome to class 24th. Okay, so today we'll go for the next concept of the homogeneous catalyst, organometallic catalyst, that is Monsanto. Okay, process of synthesis of acetic acid, very important. Okay, so this is also very important. Okay, so frequently asked in the examination. So this is also called as carbonylation of the methanol. Okay, carbonylation of methanol, carbonylation of the methanol. Okay, so as we have learned syngas, so this is what about the use of the syngas. Okay, what is that syngas? CO plus H2. Okay, so this is how whenever this syngas is treated in the presence of copper or zinc as a catalyst, oxides of copper and zinc as a catalyst, so you are going to get the methanol. So this is very much important. Okay, so this is very much important as a primitive product which we require for the synthesis of the acetic acid. So that's why syngas is very much important in this in such production of the very important products. Okay, acetic acid also is a very important product in the chemical pharmaceutical laboratory. So that's why so this is how this is how the significance of the syngas. So not only this, even petrol, fossil fuels replacement as a replacement is also this syngas is helpful. That's what we have learned in the previous videos regarding this water gas shift. So this is how the advantage comes of this. Now if you take now this, whatever the methanol is generated here, and if you treat this with carbon monoxide now with rhodium catalyst. Okay, so this it gets inserted into this alcohol and we are going to get the acetic acid. Okay, now if you see the Monsanto reaction, this whatever we are present here in the presence of hydrochloric acid HI. So this is what the Monsanto acetic acid the what you say the reaction, overall reaction is. And here what is this role of HI? Now if you see the role of HI here is, now whatever the methanol is created or we are synthesized with the help of syngas. So when it reacts with your hydrochloric acid, so we are going to get your methyl iodide CH3I plus you are going to see the water molecule is formed here. So this is what we are going to get, and very important here, which is a polar in nature. Okay, CH3I plus minus. So this is a very polar in nature, and this is very much required for our what to say the cyclic process of acetic acid. Now the catalyst used here is the rhodium catalyst. That is your this catalyst rhodium CO twice I2 minus. This you have to remember. So diiodido dicarbonyl rhodium 1. So this is in the +1 state. So this is what the catalyst used in this Monsanto process. Okay, so homogeneous catalyst. And if you see the series, so 3D cobalt, rhodium and iridium. Okay, so this is a series 3D, 4D, 5D. So 4D series, this rhodium is taken for this synthesis of acetic acid Monsanto. And you know that as down the group oxidative addition increases, so iridium is very fast oxidative addition, here little bit slow, and here it is very slow in 3D. So it is intermediate what it been chosen here. So if you if cobalt is there, so you can ask why cobalt is not used here. So if because of the iodine is taken here, so iodine become a soft, so there is HSAB, if you remember this. So soft acid soft base concept and hard acid hard base concept. So that's why the rhodium is used here because of that concept. So being soft, so rhodium and iodine is used, but cobalt is a hard, but iodine is soft in nature. So that's why this will not be considered for cobalt. That's why rhodium is been taken as a catalyst along with the iodine here. So this is how for 2 marks or 1 marks they may ask. And why not iridium as chosen for this? So iridium why not chosen? Because for the rate determining step, Okay, so since the oxidative addition will be very fast in iridium, so that will not form the rate determining step when we go for the cycle, and that's why this also is discarded, this also is discarded, and this is chosen as a catalyst for this Monsanto process here. So this is how you have to keep in the mind here. Now if you go for the simple the structure here, so rhodium CO is there, iodine iodine. So this is what the structure of rhodium is, which is in +1 state here, and this is a minus charge is here, so -1. So 2 and -1 is +1 here, and it is a type of square planar complex here. Okay, square planar complex with this, if you see, this is 9 valence electron, 2 2s are 4, 4 9 and 2, and this one, if you see, it becomes a 16 electron species. Okay, so this is a 16 electron species, and if you see the coordination number, so it is 4. Okay, coordination number is 4, and square planar complex is. Now what happened, so since it is unsaturated here, so definitely it is very good for oxidative addition here. And what is going to add here, because in previous year we have liberated, we have formed CH3I, and definitely now CH3I is going to oxidative addition here, and since it is polar in nature, so we have learnt in SN2 mechanism in our previous video that this CH3I is going to add into this in a trans fashion. So if you see that, so here I will get now CH3, and here I, and this all as usual CO I, and here I. So this is I am going to get, and since it is oxidative addition, so +1 will be changed to now by 2 units, that is +3 here, and you can see here now this is coordination number, it becomes 6, and electron count also, if you see here, so it becomes now 18 electron species. So that's why it's a perfect oxidative addition concept here will be going to happen. And since this is very slow, rhodium, as I said here, very slow, and that's why this becomes RDS, rate determining step. So in a question they will ask you in the examination in which is a RDS in the Monsanto. So this is RDS. Okay, so where the oxidative addition takes place. So this is a this 18 electron species with rhodium +3 is a coordination number 6 is RDS here. Now next step is what here, so simple, you can see here, that is methyl migration here. Next step I can get it here is what migration. Okay, so alkyl migration or migratory insertion of the methyl group here, so is going to form. So you can see here, so rhodium, so C double bond O CH3, and as usual you can see here that one CO is here, and iodine is here, and iodine is here. So like this I am going to get here. So migratory insertion does not change the oxidation state, so it's remains same here, but there is one vacant electron, and it becomes from 18 electron to 16 electron species. So this is very much important here. Okay, so coordination number 5, it becomes 5, 1 2 3 4 1 2 3 4 5. Okay, so yes, 2 yes 1 2 3 4 5. So yeah, so initially it becomes iodine is there, so here iodine is there, yes, 5. Okay, now it is correct, because here iodine we have added CH3I, so I missed it here. So CH3 will migrate here, but iodine is as usual here, so it becomes now 1 2 3 4 5. So coordination number is 5 here in this case, and one vacancy will be created. Now that will be satisfied by the incoming carbonyl here. Okay, now what will happen, so the carbonyl is going to add here, so you are going to get now rhodium, and this is carbonyl, C double bond O CH3, so this is I, and this I, and here one I. Now there is a reductive elimination. This is very much important now, reductive elimination. And what will happen, reductive elimination, this will be reduced, this will be reductive eliminated, and you are going to get CH3 COI. So this is very much important. Okay, and this part is going to be reduced, CH3 CO CH3 COI CH3 COI, and you can see the catalyst is being generated here. So same catalyst, because 2I is there, and here we have added one carbonyl here, so we have added one already carbonyl here like this. Okay, So here we have added here, so 2 carbonyl, so already here is there, and here here there is CO. So after addition of this here CO, so 1 2, and this will be migratory inserted here, and we are going to get here CH3COI, CH3COI we are going to get, and the product of these two CO and this is going to get back here. But the product, instead of CH3COH, we are getting this CH3COI, methyl acyl iodide here. So CH3COI we are going to get here. Now what happens when this is happened here? So you can see here it has been hydrolyzed. So this is treated with water here. So hydrolysis is going to take place here, and you are going to see that we are going to get our CH3COH plus HI is liberated. Okay, again HI is liberated, which is used again here for the generation of the oxidative additive ligand here, CH3I. So like this we can see that the cycle undergoes here in this way. Okay, so like this. So this is how the acetic acid is synthesized. Okay, now in simple, if I want to go for in simple, if I want to go for the cycle another way, so you can see that this is how I can show. You take it as water, okay, and if you treat this with hydrochloric acid, so again this will give you H2O. So now if you treat this with now CH3OH methanol, this will react with this HI to give you CH3I methyl iodide. Okay, now if I start this with this catalyst, rhodium COCOI minus. Okay, if I start with this, now if I take like this, what will happen? This CH3I will get oxidative added here for this to get this oxidative addition, and you are going to get this complex RH CH3I CO and I, where this is in +3 state. Oxidative addition takes place in this complex. Now if I take this like this, now what will happen here? This is 18 electron species. Now there is a migration here, methyl migration into this carbonyl, and I am going to get here C double bond O CH3. Okay, here there is I, okay, and here there is CO. Okay, so this is what I am going to get here. So again minus species here, that is your 16 electron species. Now again there is a vacant here because of migration of CH3 here. So what will happen? Again there will be now addition of CO here. Okay, again octahedral species is going to generate, and you are going to get here CH, here carbonyl will be added. So C double bond O CH3 already it is here. So one of the CO is here. So here I is there. So I and I is there. So this complex I am going to get here. So okay, so here one I is there. Yes. Okay, so I is there, and this is what again I am going to get 18 electron species here. Okay, so from 16 again I am going to get the 18 electron species with addition of carbon monoxide, and finally I am going to get back this catalyst. Okay, and by getting, so I can take it here like this. The product I am going to get is here CH3COI. Okay, so I will write, I can do like this. So I'm going to get CH3COI here, and this on hydrolysis here already this is there. So I'm going to get here CH3COOH like this. Okay, so this is how this type of cycle also you can give in a very best way, or very in a very easy way. So like this here. So this is what, so I have taken, and here you see this middle part is very much important. So water HI is very much important. So this is very much important because whenever the methanol is used, which is got from the syngas, this will react with your HI, and you see that you are going to get methyl iodide plus water is going to be this reaction is very much important. So this reaction will lead you this. Okay, now this is very much important. Whatever this is leading, it will now oxidize this to your acetic acid, and whatever this is obtained will undergo oxidative addition with this catalyst, 16 electron catalyst. okay, and you are going to get this step, which is a rate determining step, oxidative addition. And finally, you know that in previous cycle also we have learned, so this is what going to happen again, 18, 16, and again lastly reduct to elimination. So reduct to elimination, so we are not getting directly acetic acid, but we are getting acyl iodide methyl compound, and you can see on hydrolysis again whatever this water was generated here, so it will hydrolyze this to get acetic acid plus again HI is generated like this. So this is how the cycle goes on, and you can see that you can see that this Monsanto process is going to happen here. Now, in case if I go for this overall Monsanto process of acetic acid, so I can take it in the step here. Okay. So what is that? So if you take the step 1, so there is methanol CH3OH methanol treated with hydrochloric acid. So we are going to get your methyl iodide CH3I plus water. So this is what the step 1 I am going to see, that whenever methanol is treated with HI, like here what we have seen here, methanol is treated with HI, so I am going to get methyl iodide and water molecule. This is in step 3 I can take it as step 1. Now if you see the step 2 here, whatever the methyl iodide is generated, CH3I will react with now your carbonyl, okay, and you are going to get here, so carbonyl insertion is there, like here what we have done it here, so that way you can take our insertion of this we have done here to get you what CH3COI, that is your methyl insertion is going to take place, and this reaction, this step 2 is catalyzed now by my, that is called rhodium catalyst, that is your homogeneous organometallic catalyst. Okay, step 2, whatever this happening, this is happening because of the catalyzed reaction by the rhodium. Now if you see in the step 3 final step, now if you see the final step, whatever the CH3COI is formed, so this will undergo hydrolysis to form your acetic acid required, acetic acid plus again HI is generated, and this whatever generated HI is there, so it is further utilized here like this. Okay, so whatever the HI is utilized generated in the step 3 is again utilized by step 1. Again this all the 3 steps continue, and the cycle will be continued, so like this. Okay, so this is how we can explain the Monsanto process of the what you say, the the synthesis of the synthesis of the acetic acid. Okay, so this is what about this today's video. So you should know, and this also called as carbonylation of methanol sometimes. Okay, and this was done in by the name itself says Monsanto in the year 1966. Okay, so in the 1966, so Monsanto proposed this cycle of production of acetic acid. That's why it's named to his name itself, that is Monsanto acetic acid, by using the rhodium catalyst, that is your CO twice I2 minus, okay, in which rhodium is in +1 state. So you should remember all this catalyst name, like here it is rhodium catalyst, Vasaka's catalyst, okay, in the previous Wilkinson catalyst. So these some catalyst, and once Wacker's process we have used catalyst. These all organometallic homogeneous catalysts are very, very beautiful at a very mild condition. You can see that you can synthesize so many important products in the pharmaceutical laboratory synthesis. Okay, and if you see that syngas also, so in the water gas shift equilibrium you have learned the use of the syngas, the CO plus H2, which is got from the gasification of the coal and methane, how we got that, and that was one of the significance we learned. And this syngas is useful for such production of such important chemicals. Not only this, again further if it is there, we will come to know how the combination of COH2 syngas is useful in synthesis of you can say the different chemicals. Okay, important different chemical process. So this is what I think more than sufficient for you can say in this video. Okay, so go through this, and in the next video let me see if for the next concept of this homogeneous catalysis in organometallic chemistry. Thank you.